Okay, last time we talked about light, but we talked about it as a wave. And we talked about the electromagnetic spectrum and different colors of light and polarization. Today we're going to talk about light as a ray. So, the Rey model of light shows us that light travels in straight lines, and we represent them with rays, which are straight lines coming from an object. And this is an idealization, but it's really useful for talking about optics and things like reflection and refraction, which is what we're going to talk about today. So remember from our waves discussion that we draw waves as wavefronts with a ray. Now, we are still assuming that light is a wave, but what we're doing is we are ignoring these wavefronts for the time being and only looking at the ray part, the straight line that tells us where that wave is coming from. Now, light is a wave, so it obeys all of the properties that waves do. And the first one of these waves the first one of the laws we're going to talk about is the law of reflection, which we already talked about once. And it tells us that the angle of reflection equals the angle of incidence, or angle in is equal to angle out. So if I have a wave coming in and hitting a boundary at an angle of 30 degrees to this little normal line, we call this the normal, then that wave is going to bounce off the surface and leave at 30 degrees. The angle it comes in at is the same as the angle it leaves at. And light is no different. So when light reflects from a rough surface, let's say the lab benches in the classroom, the law of reflection still holds, but the angle of incidence varies, or the angle it comes in at varies. And this is called diffuse reflection. And what happens is, let's say we're talking about the lab benches, on a molecular level, this surface is not very even. It's not very flat. It has a lot of bumps in it. So even though the light will come in at a certain angle and leave at that same angle, the angles here on the surface change as you move across it. So even though the light will come in a very organized way, like these lines are, when they reflect and follow the law of reflection, they're going to bounce all over the place because of how this table is set up. And this is called diffuse reflection. And when this happens, we see the object, but we cannot see anything specifically reflected in that object. So when I look at the lab benches, I see the tables. There's very clearly light bouncing off that table and coming to my eye because I can see it. But if I stand over the table, I cannot see myself reflected in it. And that's because the light from my face travels down to the table and then bounces off in all kinds of crazy directions because the table is not smooth. However, if I were to put a mirror down on the table and then lean over it, I can see my face in the mirror because on a molecular level, a mirror is really, really, really flat. So the angle that the light comes in at equals the angle the light comes out at, but that means that all of the rays that are bouncing off that mirror are in the same direction. So the light that comes in together also leaves together. And this is called specular reflection. And this is what we have whenever we have a mirror or some kind of polished surface. So this is what we see when we have diffuse reflection. Whenever we look at any object that does not show a reflection, we see that object because there's light bouncing off it and hitting our eyes, but it's only when we have specular reflection that we can see the actual object that's over here. So for example, in the classroom, when I look at the lab benches, I can't see the lights reflected in that. I cannot look at the table and see an exact picture of what the ceiling lights look like. But I can see that with a mirror. And that's because the light coming from those ceiling lights is reflected all together at the same angle out to hit my eyes so that I can see it as one intact object. For diffuse reflection, that light gets scattered. And I can tell that there's light there, but I can't actually see a picture of the object it's coming from. Now, when you see something in a flat mirror, that object appears to be behind the mirror. So when you're looking at yourself in the mirror in the morning, getting ready for school, you're looking at what seems to be yourself on the other side of that mirror. If you were to move to the side and you saw somebody else's reflection in the mirror, it appears that they are behind the mirror. So if we imagine that the light is coming in a straight line from that object, it looks like the object is behind the mirror, some distance away. Now, we call this a virtual image. And that's because the light does not go through the mirror behind it to your eyes. It's bouncing off. It only appears that the object is behind the mirror. And it turns out that with a flat mirror, the distance between the object and the mirror is the same as the distance from the mirror to the virtual image, or where it appears to be behind the mirror. Now, we classify images in 3 ways. We classify them as real or virtual. Virtual meaning it appears to be behind something but actually isn't. And real meaning it actually is on the other side of that object. Bigger or smaller? This one's pretty self-explanatory. If you look through a magnifying glass, that is going to be a real, bigger image. And 3, upright or inverted. Is it right side up or upside down? So that's reflection. The other thing that we talked about that waves can do is refraction. And we're going to talk about the refraction of light. Now, remember that light refracts because it slows down somewhat when it travels through different mediums. So remember, when waves travel through different mediums, they will have different speeds. And light is no different. We talk about the speed of light all the time, but when we talk about the speed of light, what we really mean is how fast light is going in a vacuum. The second the light from the sun enters our atmosphere, the speed of that wave changes a little bit. And when that sunlight reaches the ocean and passes through the water, the speed changes yet again because the medium changes. And remember, whenever a wave hits a new medium and it changes speed, it will bend and it will change direction. And that's refraction. And we have something called the Index of Refraction. And the Index of Refraction is kind of going to tell us how much it's going to bend. And the way that we find the Index of Refraction is we take the speed of light in a vacuum, which is 3 times 10 to the 8th meters per second, and we divide by how fast it goes in the new medium. So this is the speed of light in a new medium. Now, when you do this and you divide the speed of light in a vacuum by the speed of light in whatever medium it is, your number will always be 1 or greater. And that's because you cannot get light to travel faster in any medium other than a vacuum. So anytime light enters a material other than a vacuum, it will slow down. So you can see the indices of refraction over here. And the larger the number, that will be the larger the bend of light that you get. So when light goes from a vacuum to air, like at the top of our atmosphere, the index of refraction is barely bigger than 1, which means it's not going to bend very much. It does bend a little, but not a whole lot. When it passes into plexiglass, the index of refraction is 1.5. So it will bend a fair amount. The index of refraction for when light passes from a vacuum into diamond is over 2. So it's going to bend a lot. And that's why diamonds are so pretty to look at. Because as the speed of light changes from the air into the diamond, the light will bend. And diamonds are cut so that when the light bends, it hits off one surface in there, and it will reflect at the same angle it comes in at. And then it will reflect again on another surface in that diamond. And it bounces around inside that diamond over and over again, according to the law of reflection, until it comes out the top and you see it. That's why they're so sparkly. So light changes direction when it crosses a boundary from one medium to another. And this is called refraction. And the angle the outgoing ray makes with the normal is called the angle of refraction. So remember, we always measure these angles from what we call the normal. And the normal is our imaginary line that is 90 degrees to the surface. So it always makes a little right angle with the surface. And that's where we measure our angle from. So the angle of refraction in this first picture is this right here. We have our outgoing ray, and the angle it makes with the normal is the angle of refraction. And an interesting note is that when light slows down, it bends toward the normal. When it speeds up, it bends away. So if light is going from air to water, when it hits that surface, it's going to slow down. And when it slows down, it bends toward the normal. And you can actually see that happen. Instead of it continuing this way, it actually bends in that way, toward the normal. But if you were swimming around in a pool that had lights underwater, the light is originating from the water, and it hits the air. And it's going to speed up as it passes out of the water. So here, instead of going straight, it will bend away from the normal because it ends up going faster in air than it does in water. Now, refraction is what makes objects that are half submerged in water look really strange. So if you have a straw in a glass of water and it looks like the straw is kind of cut where the water meets the air, the straw actually isn't cut. It's still intact, but the light waves coming out of the water speed up as they hit the air, and they will bend away from the normal, and it will make the pencil look, or the straw look like it's in a different place than it actually is. This also happens if you're at the beach or at a pool and someone's standing in the shallow end, and you look at their legs tend to look really fat and wide and short, and that's because the light speeds up as it leaves the water, so it bends away from the normal. And what it appears to us is that the light is coming from somewhere over here instead of down here. So it looks like her feet are way up here by her waist, which is why her legs look really small. Now, we can actually measure the angles at which the light will come in and out using something called Snell's law. And Snell's law uses the index of refraction and the angles to tell us what angle the light will come out at or go in at. So Snell's law is n1 sine theta 1 equals n2 sine theta 2. Remember, n is the index of refraction for that material, and theta is the angle. So for this problem right here, if we have a ray going from air to glass, we would use the index of reflection for air. So this would be air, and you would go back to that table I showed you earlier and find out what the index of refraction is for air, and you would put that number in here. And it turns out that the index of refraction for air is 1.0003. So this would be 1.0003, and it's coming in at an angle of 60 degrees to the normal. Remember, the normal is our imaginary line that's perpendicular to the surface. So it's coming in at 60 degrees. So that would be 1.003 times the sine of 60 degrees. And then that would be equal to the index of refraction for glass, which is, let's just say 1.46, because this gives us 3 different kinds. They're about all the same number though, about 1.5. That would be 1.5, and then we would have to find the angle. And this would tell us the angle from the normal of this ray of light right here. That's how you would use Snell's law. So now you're going to get some practice with it. Your homework is to answer these questions. Number 1, explain how diffuse and specular reflection are different, and which one does a mirror make use of? Number 2, why does a straw in a glass of soda look disjointed or bent where it enters the water? And 3, a light ray is passing through water with an index of refraction of 1.33 towards the boundary with a transparent solid at an angle of 56.4 degrees. The light refracts into the solid at an angle of refraction of 42.1 degrees. Determine the index of refraction of the unknown solid. So you are trying to figure out the index of refraction of the solid that is in this water. Bonus points to anyone who looks up the index of refraction and tells me what the solid is made of.